So we're going to look at lone pairs on the central atom. So we're going to organize these by electron geometries. And for an electron geometry, you can have multiple molecular geometries as you add more lone pairs to the central atom. Now, for the electron geometry linear, we don't really have any examples of molecular geometry, so we're going to start off with the trigonal planar. So the electron geometry is going to be trigonal planar. Okay, and so an example that we're going to use is SO2. So we have S, double bond, and I like to, you can do like this, or you can do without the showing kind of like that orbital. I like to draw the orbital just because it gives some space. It shows you that it's taking up more space. And then, of course, we would need to finish off our Lewis structure by putting in the lone pairs for oxygen. Okay, so in this particular case, we can see that the bond angle, which we're going to look at, is here. All right. Now, if this were a true trigonal planar, it'd be 120. But now we're going to actually see that it's less than 120 because these lone pairs are pushing the double bond electrons down. They need more room. Okay. And so this geometry that we have, so we say that the electron geometry is trigonal planar, but the molecular geometry, if we just look at the atom arrangement around the central atom, that is going to be bent. Okay. We can see bent also. There's actually two ways we can see bent. We'll do it next for water. But before I do that, I just want to quickly go to the PhET app. And we can see SO2. So we have SO2. We chose SO2. And you can see the actual bond angle is 119. Okay, and if you could look at the molecular geometry and the electron geometry, you can see there. So that's just a good example of showing you SO2. Okay, so we'll go back to, so that's the only option really for having a trigonal planar. So we go to the next, which is tetrahedral. So now we're going to have tetrahedral. So this is electron geometry of tetrahedral. Okay. And so for tetrahedral, we're going to, let's just do first, we're going to do one lone pair on the central atom, and that's going to be ammonia. One hydrogen coming out at us, one going away. Okay. Now, it was 109.5 for the bond angles for methane when we had CH4. Now, these bond angles are going to be, we don't actually, we can look at what they are, but we know that these bond angles, here to here, should be less than 109.5. Now, we're going to be a little more specific when we talk about water next, but we know that they're less than 109.5. That's all you really need to know. And we can check what they are in the PhET simulation in just one sec. Now, the molecular geometry, so the molecular geometry here is trigonal, trigonal pyramidal. Some text, older text will say trigonal pyramid, but trigonal pyramidal is the better way to say it, I think, or more common way, I should say. And so again, we can go look at the PhET app and look for ammonia, and we can see here that It's actually 107.8. I don't want you to memorize that. I just want to show you that it's actually less than 109.5. That's what we predicted. Again, we can see the molecular geometry is trigonal pyramidal. Electron geometry is tetrahedral. Okay, so if we go back and we draw two lone pairs for like water. Okay, so two lone pairs. We have oxygen, and then we have lone pair, one hydrogen, another hydrogen. And then we look at the bond angle here. Water is special enough of a molecule that we're going to actually need to know this is 104.5 degrees. It's lower because it's got the two lone pairs pushing down on those bonds. And so what we know is that the NH3 is less than 109.5 but greater than 104.5, which makes sense. It's kind of in the middle, 107.8. And so we can go and write the molecular geometry here. So the molecular geometry is going to be also bent. So we have two molecular geometries that have the same name, both for this SO2 molecule as well as for the water. So look, I know we didn't, bent's kind of not a very technical anyway, but anyway, that's what it is. We can go to the PhET simulation, find water, and we can see that if we arrange these, we got, whoa, here we go. We got the 104.5 showing that bond angle with a molecular geometry event. Okay, so now we can move on. That's all we can do for tetrahedral. And so the next electron geometry that we're going to look at is trigonal bipyramidal. And this is the electron geometry. So for this electron geometry, we're going to have, so notice that for the trigonal bipyramidal, or sorry, trigonal planar, we had one. When we increased to the tetrahedral, we had two. We're going to have three different electron geometries here. So we'll start off with SF4. So SF4 has a geometry. So we're just going to add one lone pair. So remember, PCl5 was our example where we had this 3 in the plane. It was SF4. Again, all of these fluorines have lone pairs. We tend to see fluorine a lot for these hypervalent compounds, and it's because fluorine is very electronegative. It removes some electron density away from the sulfur, making it much more stable. Okay. And so if we look here, this particular shape, you might not be able to see it, but it is, it has, if you put it on its side, kind of looks like this. And so the molecular geometry is seesaw, which aren't as common on playgrounds anymore because of lawyers. They ruin everything. Sorry if anyone is aspiring to be a lawyer or has someone in their family that's a lawyer. And then the bond angles here, we have two. Remember that we had the bond angle between this bond angle. It was 90 degrees, and so now we say it's less than 90 degrees. And then the bond angle between the sulfur, fluorine, sulfur, we're going to say it's less than 120. Okay. Now we can go back and look for SF4 on our PhET simulation. We see SF4, and we can see here that this is the, you can kind of see the seesaw. If we do it this way, like this, here's our seesaw. But you can look, and let's orient it like I have it drawn. Okay, so we can see that we got this 87.8, and then this angle right here is 101.6. Actually a pretty big difference from the 120 that we predicted, so a lot lower there when you have it in the plane. So all you need to really say, though, is less than 120, and that's perfectly fine. You don't need to memorize those. So that's the molecular geometry of seesaw. Now let's take two lone pairs and put them on the central atom. If we do two, that'll be CF3, or sorry, ClF3, which you might be thinking that's a little weird. But just go with it, it's fine. So now we have two lone pairs of electrons here. Okay, so this particular molecule, if we look at the bond angles, now we really got, so we don't have any bond angle with this, so the only bond angle we have is between the central atom and the either top or bottom, and that's going to be definitely less than 90 degrees. We don't have any bond angle of this fluorine in the plane that's like close to less than 120 because there's two lone pairs. We can't really make a bond angle there. And so this has, if we turn this on its side, it has this this T shape. So we call it T-shaped or T-shaped. That is the molecular geometry. And let's see if ClF3 is on the PhET simulation. I think it is. There it is. So yeah, they just call it T-shaped. I'm not sure if we spell it out, but you can see here that the only bond angles we can show are between the top, this top one, and the bottom one here, or the equatorial, or the bottom, and this one. We can't really do one in between because we have two angles here. So the only angle is less than 90, and you can still see it's not. These both are kind of pushing equal. So if you look here, this non-bonding pair electrons and this non-bonding pair electrons are both pushing equal on this one chlorine, or this one fluorine. So it doesn't really displace it that much because it's got kind of pushing in each direction equally. Okay, so go back to here. Last one that we have for this trigonal bipyramidal electron geometry, so we have three, is 3 lone pairs on the central atom, and that's actually going to be for the I3. Getting real weird now. So we got the lone pair, lone pair, lone pair. And so that's going to look like, if we were to do this without the bubbles, it would look like in the plane, out of the plane, going away. Okay. And so if we look at the bond angles here, the bond angle is from here to here, so that's 180. And whenever you have 180, that is a linear molecular geometry, or any type of geometry. So linear pops up twice, and so does bent. But linear is actually an electron geometry and a molecular geometry, where bent is two different types of molecular geometry. So a little different there. Okay, so the last bit is going to be for the octahedral. So we're looking at the electron geometry of octahedral. And so remember, that was like SF6, and so we have 6 things attached. So we remove one and make it 5. And that's going to be SbCl5. So Sb, and we're going to have Cl. We're going to have Cl coming out, Cl going away, and then lone pair on the bottom. And then putting those lone pair electrons here, all the way around. Okay, and if we look here at the bond angles, we're going to have this lone pair electrons kind of pushing everything up. And we kind of looked at this at the intro video to the sim. So this is going to be, these angles are going to be less than 90 degrees. And then also, if we look at the bond angles here, we can check and see. Let's just do a quick check and see what they are. So let's go to our SbCl5. Do we have SBCL5? We have BRF5. That's good enough. That's the same. So if we look here, we see that all angles are about 85. So, well, so sorry, they're about 90, a little less than 90 for the 4 on the plane, and this definitely is getting pushed up. It's a little smaller. So what? So it's a little less than 90 here, but you should see that because we're seeing this equal pushing in all directions, that the angle that we see between like this atom and this atom is still about 90. It's a little less than that. So to keep things simple, what we can say here is that this is less than 90 and that these angles are also less than 90 degrees. And that's fine. That we do see more pushing kind of coming from pushing all of these up so that this bond angle is a little less than of the 4 in the plane. The molecular geometry here is square planar. Square planar. Okay. And then we have oh, sorry, not square planar. Just kidding. It makes a pyramid. So we let me just draw this. I'll show you. SB. So it's got here, 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 here. So and these are CLs. And then we have one CL up top. And so if we look at this, it's got a square. So it's square. And then it makes it, if you connect all 4 CLs on the outside of the top one, it makes a pyramid. So that's why we call it square pyramidal. Okay. And then the last movement we can do is where we add 2 lone pairs. And so we can use XE, then F4. So that'll actually be lone pair, and then put the 4 Fs here, 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 and then lone pair on the bottom. Now in this case, because we have equal kind of pushing up and down, the bond angle that we find is still 90 here. So this is still 90 degrees. It's the only one that we don't really see being changed because, you know, these are kind of pushing down the same way these are pushing up. So we don't see any displacement of our bond angles in the plane where the atoms are. So the molecular geometry here is square, and then it makes a plane, so it's square planar. Okay, and now we don't actually start adding more lone pairs to the central atom because it's very hard to find atoms that can actually have that many electrons on them. And so you notice that we have like SB and XE. These are going to be down in like the 5th row because they can have expanded octets, because they're more stable, more electrons. Just really hard to find things that you can just keep loading with the lone pairs on the central atom. So even though we could try to remove another atom, put another lone pair, we just don't see it often making stable molecules. So we only have 2 options there. So those are the different molecular geometries for the electron geometries for octahedral, for trigonal, bipyramidal, tetrahedral, and for trigonal planar.